Welcome back to my LeetCode Visually Explained series. Today we're going to be going over LeetCode number 11, the container with most water. But before we actually get into the code, one thing I want to go over with you guys is the bottleneck to this question. So when you sit down and really think about it, you have to remember that the bottleneck is always going to be the shorter wall. And why does it work like that? That's because the liquid is going to always go over the shorter wall. Just think about how water works. If there's one really tall wall, but one really small one, water's not going to magically just start floating up because there's one tall one. The small one's going to obviously be where the water flows over and onto the ground. All right, so let's jump into the easiest solution first, the brute force approach. So first, what we're going to do is we're going to define our function max area with an input of heights. Then we set up our outer loop for I in range, the length of heights, to grab our left wall. Inside of that, we run an inner loop, simply for j in the range of I plus 1 length of heights, to scan every possible right wall. For every pair, we calculate the area, the minimum of heights I, comma, heights j, times j minus I, and update our max area variable. But watch this. For just 9 walls, we execute 36 comparisons. Scale that to thousands of elements, and this is now an O of n squared problem, and the runtime completely chokes the CPU. Alright, so if you watched my last video, you'll remember how we talked about most LeetCode problems being broken down into just a few simple patterns. Well, what do we actually need to eliminate this O of n squared bottleneck that we've hit? We're going to deploy the two-pointer pattern, and here's exactly how this works. We place 2 pointers at the extreme edges, guaranteeing our maximum possible width. Now here's the secret to the entire algorithm. Why do we only move the shorter wall? Well, think about it like we said at the beginning. If we keep the short wall and move the tall wall one inward, our width shrinks. But our water level is still bottlenecked by that exact same short wall. The water is just going to flow over. The area can only decrease. So, by discarding the shorter wall, we mathematically eliminate all useless pairings. Alright, so now with that explanation of why the two-pointer pattern actually works for this question, let's write out the actual optimal Python function line by line. So we're going to start off by defining max area with an input of heights and initialize our 2 pointers, left pointer at 0 and left pointer equal to heights, the length of heights minus 1. Then we drop into a while loop, and it's going to be while left pointer is less than right pointer. Inside, we calculate our area. We have minimum of heights of left pointer, comma, heights of right pointer, multiplied by the right pointer minus left pointer. We update the max area is equal to max area, comma, current area. And we take the maxes of those, which is why we have max there. Then for the pointer shift, we have if heights of left pointer is less than the height of right pointer, we do left pointer plus equals 1, or else right pointer minus equals 1. This is so that we increment right if the left pointer is smaller, or we increment left if the right pointer is smaller. Then we return max area after one clean O of n linear pass. We don't need to run the code over and over, just one simple time. So where do you actually see the two-pointer pattern used in real life production? Well, beyond just LeetCode, this is the exact logic used in low-level systems for memory compaction. Garbage collectors deploy 2 pointers, one at the start scanning for free space and one at the end finding active blocks, swapping them to compact memory of in O of n time without allocating extra RAM. By mastering this, you're not just solving a puzzle, you're proving you know how to optimize both CPU cycles and memory overhead in real world architecture. See you guys in the next LeetCode question. I really hope that this gave you guys a little bit of a visual explanation to this, as when I first started doing this problem, specifically, it was hard for me to wrap around why we were just moving the smaller pointer. And once I got it, I wish that I had seen a visual like this to help me, and I hope that it does the same for you guys.